as well start. So welcome to this last session of the conference, and actually last session of this whole program. And the first talk is by Andreas Svedin, who did his Master of Science degree in the University of Uppsala in 2006, and has since then been a graduate student at the University of Columbia in New York. And he lists as his interests at some webpages, for example, exoplanets, habitability, solar granulation, the solar cycle, patterns in CMB, chaos, non-linearity and turbulence, and in particular the connection between chaos and chaos theory and astrophysics. So today the title is Nowcasting the Solar Cycle Using Low-Dimensional Models. So please go on.
Thank you. So that is, of course, the effect of having a supervisor called HB, or because you have projects all over the place, and you just have to learn a whole new field to answer particular questions. So thank you for having me, and yeah, let's go. So a short outline. So we're gonna speak about the solar cycle. So first some notes about the data, and then some ideas of how to construct models. There are basically two main approaches that I'm going to try to differentiate. One is the dynamo construction, which is basically starting from physical equations, and then you get a model, and then you see if it fits the observation. Or you do the other thing, which is astromathematics, which is you start with the observed phenomena of the system, and then you try to figure out the math, and then you figure out what physics actually that corresponds to. That's two different approaches to doing low-dimensional models.
What is PSD?
It's the Platt-Spiegel-Trésor model, which I'm going to explain, which is the currently it is one of the currently the best low-dimensional model for capturing the solar cycle, and we are looking into finding other ways to develop this.
But maybe best in the same way of the best planet five.
Yes,
best
available. So yes. So this is the classical sunspot observation. It goes back a couple of 100 years. It's basically from 1750. We do have monthly data, and before that we have more spares. And here we see the main features, which is the 11-year cycle in terms of sunspot numbers. And then we also see some kind of modulation on some longer scales, like this. And then we can also see that we have also a bigger modulation like this, that we are in the so-called modern maximum here. And then we also find this Maunder minimum during the reign of Louis XIV, Sun King. And we would like to have a model that kind of captures all these kind of features to get something that captures these kind of features, and hopefully see if that actually is useful to go into the future.
Is there any reason why these are red crosses instead of blue? I mean, are the observations qualitatively different? Are they made in a different way?
I think these crosses are the actual observations, whereas this is a much more dense observation. This is monthly values, and these are the actual observations. So we have these are the available observation, and this is kind of a continuous sequence of observations.
Yeah, the red ones are after the fact. People went back and looked for places where there were observations.
Yes.
As opposed to people observing the sun semi-regularly.
So this is also a plot. We see here the blue, which is the sunspot observation, and the sunspot is The sunspot number is the Wolf sunspot number, which is a combination of the number of sunspots and the number of sunspot groups. And that's just a way is a convention which is used to calibrate different observations. And we also see that this variation on the NM here also is kind of close to other more physical variables like the radio flux or solar flare index or irradiance. So even though we only have this blue line back 250 years, it's plausible to say that the blue curve tells us something about the general physical behavior of the sun. So here we have the smooth mean monthly sunspot number since 1750, and that is kind of the quantity that people in solar cycle prediction is using. So if you want to predict the next cycle, the one that comes here, number 24, you should predict it in terms of the number of the peak value, and here we see the peak values. So
that's just the maximum of those.
Yes, it is the maximum of this. They correspond to this. So here we see the monthly in black, and on top of that we see the red, which is the 13 months running mean, which is the smooth thing, and it might be easier to see here. Here we see the monthly in blue and the smooth in red. So yeah. So if you take the sequence and you do attractor reconstruction and try to see, is there a pattern? And this is the Spiegel-Wolf paper from 1987, and this is basically junk. It's nothing you can see. But if you smooth it more, it starts to get some kind of shape.
So what is actually?
So this is if you do delay or reconstruction. So if you have a time series, so you have xi, and this would be xi plotted versus xi plus some delta. So it's a normal attractor reconstruction feature.
So you have xy on one axis, I plus 1 on the other.
With a delay.
With a delay, yeah. And what is the data plotted? Figure 1. Is it the maximum value? Or
this is the. I think this is the year, the monthly value for the entire series. And when you smooth it, it becomes some kind of thing here. Smoother. And here they use the Bracewell formula, which is that instead of having a 11-year cycle, then you have a 22-year cycle. So instead of having a cycle like this, it's actually so this is a negative and this is a positive cycle, and that is because the reversal of the magnetic field is really something that looks like this. So when you look at, when you flip every other cycle and smooth it, you get something like that looks like this. And if you smooth it even more, you have something that starts to appear to be some kind of pattern. And if you smooth it enough, it will become a limit cycle and eventually a point. So you have to figure out, what do you want to model? Do you want to model this? Or do you want to model this? Or do you want to model this? That's basically the question. So there's some indication that the solar cycle is low dimensional. There's a lot of people that have taken the solar cycle time series and then said, we have estimated that the correlation dimension is 2.6. That is, of course, a dubious business to do with short and noisy data. But there is there is consistency in terms of that some get 2, and some get 7, and some get 5, and some get 3, and using different methods, they all seem to agree that there could be something on the order of less than 10. So I think the result here is not that it's 5.2, but it's sufficiently low dimension. It's an indication that
from the dimension calculation.
Huh?
You think that from the dimension calculation?
I think that the dimension calculation indicate that it could be something low dimensional. Nothing
Dimension
more than that.
calculation only indicates that you've got about 200 years of data. Nothing else. Nothing else at all. There may be other reasons for thinking low dimension. The dimension calculation is not one of them.
So the usual argument against this is that they don't get a consistent result, and that's
Well, that may be the usual argument. But the basic argument is if you've got about 14 periods of something, you will get a number of less than 5. And if you've got about 14 periods, so from the dimension calculation, there may be other reasons for thinking that it's low dimensional. But just the dimension calculation isn't one of them.
Okay. There's also looking at the number of significant eigenvalues in single-valued composition and so forth, and they all seem to have a roughly
So
7
it's high-dimensional data when you take about this many oscillations. Any data. All those tests give false positives. If you take the turbulence, you give me an oscillating regime for turbulence, give me this many oscillations, and you'll get a number like those.
So that's why we go to the second one. And the second one is, in solar physics, there has been a lot of low-dimensional toy models that in certain ranges capture some kind of features of the solar cycle. And someone said that this is actually a much better estimate of the dimension. That if you can make a model that captures the behavior, you have actually shown that. Who was that? Was it you?
Yes, but the conjecture is that if you have enough to do the one on the, the amount of data you need to do the one on the bottom is orders of magnitude less than on the one on the top. So that's right. That's why, yeah. So if you can show that it captures the dynamics right,
Then sufficient.
then that's much more informative.
So we should formulate the gain. We want to formulate a model in terms of variation of the suns, but no. In particular, we want smooth, thin, or bin. I don't want to go into what is the best. I think thinning and binning might be better than smoothing. The point is that the target value is in terms of the smooth one, so we might want to do the smooth one. And we want to construct a low-dimensional model, less than 10 dimensions, because that is, we can treat that reasonably on. There's indication that it might actually work. So this is kind of where we are now. And then we want to select parameters using the ignorance method or the JD or Judd-Smith filter, as we have been speaking about for a couple of weeks. And we also want to construct ensembles and evaluate their performance in sample to be able to finally make a prediction. And then we also want to figure out what do we actually mean by a prediction. Should we give a number and an error bar, or should we give a distribution, and so forth? It's unclear. So the first approach is to go from astrophysics. You express the components of the systems in mathematical terms. You are writing up the equation, you are simplifying it until it becomes sufficiently usable, and then you see if what you get out actually fits the observation. And a typical step here, of course, is to go from PDs to ODs or to the one-dimensional model. So a case of this is the Charbonneau 2001 picture, where basically we have this is the back of Leighton picture, where the toroidal field is generated by the poloidal field in the previous cycle, depending on the differential rotation in the takt time. So this is the outer 30% of the sun. There's a circulation here, and there's shear here in this layer, and this generates the toroidal field. And then when this migrates here up with the sunspots in this picture, it generates the toroidal field by some function depending on the previous toroidal field. And that means that you can combine these two expression into some relation between the previous toroidal field and the next toroidal field. And then you can express this function in something that looks like the logic map and see if you can capture some kind of feature of the solar cycle. So this is typical output of the Charbonneau A and Charbonneau B. So this is Charbonneau A and Charbonneau B.
What is S?
S is now the sunspot number, because you say that the sunspot number is related to the toroidal field. So it looks something like the solar cycle, but my
you want this to be the maximum number?
Yes, this is the maximum number of the solar cycle. When you try to fit this to real data, nothing really works. But it kind of gives a picture that this low-dimensional pictures capture some of the feature we observe, and especially it was constructed to find the odd-even behavior that every other cycle was smaller than every other cycle.
Was it like that? Could you just show the yearly the real data?
So there's a picture which is the odd even.
Yeah, the next one. No, that is.
So there is you see that these two are higher than these, and these two are higher than this. This is so low, high, low, high, low, high, and that's kind of a picture which has been argued as one of the features in
I
the
thought you had a curve where you have only the maximum points. Some other
yes.
Yeah, this
here.
one. This one. This doesn't look like an alternating.
So if you plot the mean here, I think you see
is
that.
Maximum points. This doesn't look like alternating.
So but if you plot the mean on top of here, the picture is that they end up on either side of the mean. That is kind of the picture. So yes. So this.
Anyway, that is the curve that this should resemble.
Yes. And they kind of look good, but quantitatively or when you try to fit it and convert it, it doesn't really work. And of course, it could be that I haven't figured out the best way to do it. So this is the other approach, and that is that you observe some behavior in the system. So for example, Eddie in '57 saying, "Oh, there actually was a moderate minimum." So then Ed and his friend said, "Okay, we have to figure out a way for the sun to actually do this thing." So we figure out the thing called on-off intermittency, which is a way of getting oscillator to have a flat line at some time. And for this to work, you actually have to have an oscillating layer in the sun. And that has to be something in the boundary between the convection zone and the radiative zone. So basically, this picture from this observed thing, we both get a mathematical structure and some implication for physics that there should be such a layer. And now we of course have found this layer in with Helios epistemology.
But why do you think it implies that there should be a lepton?
Because the on-off intermittency needs a oscillating. It needs a oscillator, and you can't have a regular oscillator in the convection zone. Therefore, you have to have it somewhere else. So let's say in the layer in between, and these of course comes that these are earlier than these, but that is only with the Hall application date, and really this picture kind of came together. So
where is the time line?
It is the layer between the radiated here.
The base of the convection zone.
Yeah.
So when you say there's no oscillator in the convection zone itself?
But you don't have a regular oscillator. This is typically chaotic, and this is typically it can be seen as a regular oscillator.
But I mean, so this inference seems to be then is that because you have a regular oscillation, there must be a checker cloud, not because this oscillator or not is on or off.
No, because as
So
I said,
why exactly do you need this clock? What is it that needs? What is
so to get the grand minimums
out of?
in the sun.
So clearly, to get the grand minimum in the sun, you don't need the clock, right? Is there a restriction on getting the on-off intermittency?
So
This particular model that you require, that requires this background clock.
So you can of course try to figure out another way of describing this phenomena. So I think we go to the model that could be helpful. So here we have nonlinear oscillator where the W is related to the linear circle, and the B parameter is related to the stability of the Hall by location. And then we have a coupling constant between this system and a regular chaotic system. This is the Morse formation of the Morse-Spiegel system. So if this is the convection zone, it's chaotic, and then you have a regular oscillator coupled with this thing, then you can get the kind of feature we see in the solar cycle. So, for example, here, this is the output from the system, and you can get these oscillations, and on longer scale they. So this thing is one of these, and you can also get these grand minimums because this construction generates when this threshold is reached, you go into off intermittency and then on intermittency.
What variable is shown here?
Huh?
What variable is shown here?
So this is time, and this is the x squared value. So this one. You can also do a thing of saying that the sunspot number is a combination of this plus this in a similar way as the Wolf sunspot number is reflected. So with this, you get this thing which looks surprisingly good. So if you add more, if you couple this to there's two approaches. One is to add noise to get the more jagged features, or one can add an additional chaotic system to get the small scale modulation. And then you get here, this is basically the long-term behavior of this system with random minimums. And here we see two of these cycles, and this is just the sampling rate. So here we have thin more than here. We just plot a few, and this is how the solar cycle looks. And we see that some of the features of the solar cycle, especially this Nevishev gap here, which is interesting, and then this juggedness, and there's also a knee here, which is found in the solar cycle, which actually appear here. And to get this nice square row the thesis, and by hand basically went through parameter space to find these nice plots. So what next? This is what we want. And of course we could...
This is observations.
This is observations. And this is basically the general trend. And then we have added a shunted disk, a Lorentz system on top of this. So basically we have a Lorentz attractor that goes back and forth, and that generates this very nice knees
So what's on the
and irregularities. This is time and sunspot number, simulated sunspot number.
So this is thousands of years.
No, that's iterations of this thing. And of course, you say that this range is 11 years, like a cycle. So this is a cycle, and this. The problem is that to integrate this, you have to have a very high frequency of the Lorentz system, and that is very computationally annoying. And also you have you go from like 8 to 11 free parameters, which of course is annoying. So
are they coupled, or are they just summed for multipliers?
So these are coupled through the sunspot number.
Different Lorentz trajectories will affect what happens in the future for your sun.
No, I think this is just, in a way, added on top of it. So one way is to do this, and the other way is just to add noise. And it depends on, and this is much more computationally expensive. So what I have been trying to do is to try to use a low-dimensional model 3 and try to capture some of these rugged features and see if we can actually explicitly fit these features which we see in the solar cycle with some kind of low-dimensional model.
What is so important to have this?
So,
Sure.
So of course you could do the thing of just do the cycle fit like this and say that we are only interested in the feature here. But we are also interested in when does these things happen? When do we go into grand minimum? And I think that when my experience of looking at these things indicate that there is a correlation between how these peaks and knees and stuff works, and when we actually have these big and semi-big minimums. So if we can interpret these features in terms of state space behavior of the system, we could use that to better predict and maybe figure out what kind of precursors appear to be before a grand minimum, for example. So that is what I'm playing around with, but the game, of course, is to try to capture not just one main feature, but several main features with parameters. So, and then, when this is done, what should we do then? We should use the gradient descent ignorance thing, which we have been speaking about this week, for parameters, say, election. And that automatically gives us an ensemble, as we just have explained. And we know that this works for low-dimensional systems. We have tried it out and it works fine. And this can be used as model construction feedback. So if these parameters doesn't fit well, we can use that information to figure out where to update the models. And this feedback of developing the model and also evaluate the model error is something that really hasn't been explored very much, but could be a very interesting way of refining the models. And we also need to validate the forecast in samples. So take the first 150 years and try to predict the next and see if it works in sample. And then we need to make a prediction. And when I make a prediction, I can cut my hair, which is excellent because I have a back with HP. I can't cut my hair until I have made a prediction. And then he said that.
You look like Lenny.
Yeah, because Lenny tried to solve this problem in '85, and that is why we are still here. But it's interesting to figure out, what does this mean? What do we want to do? Should we say it's going to be 154 and a error bar, or should we give them a distribution function, or should we give like what is reasonable? What is the most useful thing to know? And I think that what is expected is to have a number with a error bar, but there might be more informative ways of actually presenting this prediction in a way that people actually can use it, because the value of the next circle is of importance to satellite people and telecommunication people and power grid people and so forth, because you want to know how big shielding you have to have on the space correct, so the forecasting doesn't get right. So that's that. Yes.
So how this basic frequency, how short is it? I mean, is it, you have almost exactly the same period, or is it, sometimes 11, sometimes 12?
I think it goes from like 9 to 13.
Between 9 and 13 years. So it's not very short.
It's not very short. And of course we have the current example of the current cycle, which has been a very long cycle. And people wonder if that implies that it's going to be a grand minimum and so forth. So the plan is to exchange these with what is a very regular thing, which is just modulated in the amplitude to something that looks like this, which maybe could tell us that this cycle is longer than this cycle. But then again, the problem is that is this one cycle and this one cycle and you have to be clear what you actually mean when looking at this. So when you do this, you have a clock. A clock which you modulate in the Lorentz system. And if you want to go beyond something like this, you have to get some kind of picture.
I mean, if period isn't really constant, then it may not be an oscillator at all. I mean, I don't know if you've heard of something called the QBO in the atmosphere. That is, you know what this is?
The
Biannual oscillator.
biannual oscillator.
Yeah, I mean, this is alternating directions of the wind in this stratospheric probability. There is no oscillator there, but you have a fairly regular pattern. I think it's like between 25 and 30 miles.
Yeah.
There is no, I mean, you don't have any oscillation in the sense that you have, you know, a force and back reaction and inertia or anything like that. It's just, well, it's driven by wave form.
So
It's, I mean, the period is rather in an effect of how strongly you force it.
So,
So it might just as well, I mean, it might be that you shouldn't actually have equations with, I mean, the basic here, you have an oscillator, this omega here is an oscillator. In the case of the QPO, to model that, you don't have an equation, you don't have an oscillator.
so I think the point is that this thing kind of came first,
No.
and that implies that there should be something in the sun, and actually we found it in the sun. So it actually is here. So in a way, in a way, if you can do it without an oscillator, fine. But the oscillator gave us a clue that there should be something interesting here, and we found it. So in terms of that, the oscillator was a very good guess.
I mean, how would you actually distinguish between whether there's an oscillator or not?
I mean, I guess this solar cycle is the strongest sign that there is an oscillator.
Yes.
Yeah.
So how do you know that there is? It seems like you're saying that this has been confirmed. What confirms the existence of real oscillator?
So of course, this is a picture. This is a cartoon. Of course, there isn't a pendulum there, but it's a picture that kind of captured the behavior and explained how it could work. In reality, of course, it doesn't work like that because we have zillions of degrees of freedom and they do lots of crazy stuff. So in reality, it doesn't look like this, but it's an illustrative way of looking at it. And the question, of course, is does this picture, this illustrative picture, actually work to construct a model that actually works to predict? Because if it does, that is a very strong case that that picture is actually good. If it works, it shows that it actually exists.
It's a bit good as in useful, not necessarily good as in true. I mean, wouldn't you agree? You could say that you've got this modeling framework that requires an oscillator, and therefore if that framework turns out to have good empirical properties, that in some naive realist sense makes you think there may be an oscillator in the real system. But the real constraint is because the particular theoretical approach you're applying requires one, not because you actually believe there is one in the sun. You need it for this modeling approach. It's the model that justifies it, not your belief that there is one. Or is it your belief that there is one there?
So but the way to check it, if it works and if it's a very good model in predicting, that indicates that the model is probably quite good and is useful. What actually happens in the sun is of course, if it can say anything about
Yeah, sure, if you can really predict with the model, then.
Well, and show it's unique. So If you could really predict with the model and show that you can't predict without a model which has such a clock, then you could argue. But as it is, it's just a model construct.
Yeah.
Like the Hadley cell. The Hadley circulation.
If you look at the statistics of these signals,
Yeah.
of course, I mean, just frequency analysis,
Yeah.
I guess you have a pretty short peak,
Yeah.
not better, and do you see anything else? Or do you see something particular from the autocorrelation function?
So-
those things.
So this is of course extremely well studied.
Yeah, I know.
You find it in like every
So what does it look
physical.
like?
And you kind of have I think as we spoke about previously, I think we have the 11-year cycles, and we have something, and then we have a big peak at 11, and then we have the 22, which is a kind of thing, and then we have a gap at 44, I think, Axel said, and then we have the 88 thing, and then we have a 200 something. And that of course calls for interpretation of period doubling and so on. But this is a kind of a picture that you find from so this is 11, this is 22, and I think Axel said this maybe
Where is it?
I think it was one of the first long autocorrelation functions computed. So you will basically develop AR1 processes from this, and then showed why, in fact, because the solar cycle is nonlinear, the AR1 process can't really be an AR1 process. In 26, and then statisticians in the 40s sort of forgot that. But
so this is an indication, but the question is, so it's an extremely well-studied system, but there is the only thing that people agree on is that they don't agree on it.
There should be another one less than 11 years.
Yes, of course. I think you have a short one here at a few hours, and then you have discussions about some kind of monthly thing, and then of course you have a rotation of the sun, which comes here, which should give you 1 month. And of course,
3 years also.
yeah, okay, we have a 3-year thing here. So yeah, we have a lot of.
So the whole cycle is, we'll actually define the cycle after almost something like 16 or 17 years of data. Not even 2 oscillations. So there's lots of stuff.
Yeah. And our second speaker.
Yeah, I'm supposed to be Michaela Kajan.
She's not here, and she has not responded. She gave me a title and everything.
Yeah, but I just,
It's her or what?
I'm not sure, but I saw something like her walking.
Yeah?
They're out
Today.
They're outside like a couple of hours ago.
Couple of hours.
I'm not sure. It might be a false observation.
False positive.
Not because I was expecting.
But the family be one.
What we could do is,
I did family.
she has responded, yes. And I just hear that from my email that it was not that long ago, that I didn't respond to her. She gave me a title and I thought everything was okay with that. I didn't say that. I was wondering if there's interest to discuss a little bit more the solar cycle. I could run down a presentation that I have. Would you be interested?
Sure.
Then maybe. That is a presentation that I had a few weeks ago, 6 weeks ago.
So it wasn't playing.
Okay. In that case, of course, already. actually I'm surprised that it doesn't react now.
She came to us yesterday. I don't think you.
No, I haven't seen her. I mean, but I emailed her now, an hour ago or something. So, anyway. Maybe it doesn't. Yeah, it did. In which case. Very strange, because it's normally always extremely random.
So statisticians care about sunspots about the same amount that they care about things like the Canadian lynx. Long time series that are hard to model. Why do
Canadian lynx.
this large cat that they have data over several hundred years for Canadian trappers who go out and try to kill bear, beaver, lynx. So it's just one of these standard time series you always see. But why do physicists care about sunspots?
They are an indication
And not lynx.
why we care about sunspots. I mean, there's first of all the necessity that people need space weather information. That's why they look into sunspot first. It would be ridiculous to go into space without knowing whether anything dangerous is coming up. These are extremely dangerous events when you have them. And whether anybody would ever dare to go to the moon with our knowledge that we have nowadays is actually not so clear. I mean, it is a suicide mission in some sense.
Were they actually timing the moon missions for solar minimums? Do you know that?
No, not at all.
I don't think
It was more like maximum.
solar cycle was going to be in 1963.
It was more like maximum. No, it was complete ignorance at the time. So it was really a matter of luck that nobody got killed.
But it's also
What happens to so there's a solar flare or something?
Yes, or even more strongly, so-called coronal mass ejections. So